All right. Hi, my name is Darek Stojaczyk. I'm SPDK core maintainer at Intel, and I will tell you about flexible and dynamic resource use with SPDK. First, we'll start with some technical overview of architecture. So we'll give you some overview into we'll tell you why we're doing some of this resource management. Then we'll go through all the cool memory management stuff, so all the features that have been merged over the last year. Then Ben will talk about threading model changes that are in the middle of being merged right now. When you have a memory address in your application running on your CPU, it's most likely a virtual address, and it's called virtual because it doesn't necessarily point to a single physical location in your physical memory. So in your RAM, in your DIMMs, whatever. The physical location of that memory, so the data in your physical memory can be relocated to different locations, and that's being done to defragment memory, or the whole data can be also swapped out to a disk if it's unused. And it's all transparent to your application. There's a memory management unit in between CPU and memory that takes care of the translation. And that's totally fine, unless we want to do DMA on peripheral devices like PCI NVMe. So PCI NVMEs, they talk to memory bus. They're using directly physical addresses. They don't have anything like memory management unit. So on Linux, you can retrieve physical address for your virtual memory buffer at any point of time, but you can initiate a DMA transfer on that physical address. So you can put that address into your NVMe request. You can put that request into your NVMe submission queue. You can ring the doorbell, and most of the time, I guess, the DMA will work, but sometimes the physical memory can be, the physical location of your data buffer can change, and what was previously describing your data, your memory buffer at some given physical address, maybe now pointing to completely different data. It might be a kernel structure, it can be anything. So if your NVMe does DMA, does some writes into this physical location, you may end up corrupting your system memory, and you don't want that. So in order to do DMA from CPU, from user space, you have to somehow pin that memory. Make sure that the virtual buffer is always backed by the same physical pages. Yeah, and it happens that there is no cross-platform way to do that. Actually, there's no defined way to do that on Linux. You can call mlock, but that will just prevent the memory from being swapped out to a disk. It will be still possible for that memory to be relocated to different physical location in your RAM. And we use huge pages to work around this problem. I'll talk about this in a second. Now, so I said there is no futures. There's like no defined way to pin memory. And we work around that, but the future-proof solution is to rely on the IOMMU unit on your IOMMU unit in your CPU. So that's just like there is a memory management unit that translates virtual to physical addresses. There can be same unit for peripheral devices that translates virtual bus addresses, let's say, IOVA, IO virtual addresses to physical addresses. So in this model, we don't even care about physical memory locations because we've got it all abstracted away. So from CPU we use virtual addresses, and from the NVMe part we use I/O virtual addresses. We don't reference physical addresses at all. IOMMU is programmable from user space. So inside SPDK we can assign any arbitrary bus address to any single virtual buffer. So if you want to do any I/O in SPDK, you have to, like, if you want to call SPDK bdef read-write on NVMe bdef, or you use SPDK NVMe namespace read-write, you have to provide it with a DMable buffer. And how to do this? How to retrieve that buffer? The simple answer is to use SPDK malloc. It's just like POSIX malloc, but instead it allocates DMable memory. So you provide it with any size. It can be any arbitrary size of the memory you want to allocate. Yeah, and in this memory will always DMable. We achieve that by backing this memory by huge pages. Yeah, they are actually, it just happens that they are never relocated to different physical memory pages. They are never swept out to a disk. So, well, they appear to be pinned. However, huge pages are likely either 2 megabyte or 1 gigabyte in size. So there needs to be some kind of resource, memory management to split those huge pages into smaller allocations, or combine some huge pages to do bigger allocations, bigger than 2 megabytes, for example. So SPDK malloc memory is also shared between processes in a multi-process group. That's just a cool feature of SPDK malloc. We won't go into too many details on that. Okay, so that's how memory management worked a year ago. It's DPDK that does most of the work here. So a year ago, when you started your application, you had to provide it with the size of memory you will be going to use in your SPDK application. So you had a bunch of huge pages pre-reserved at initialization time. And later on, you could still do dynamic allocations, but those would be, backed up by those huge pages allocated at initialization. So if you wanted to use more memory than you originally reserved, your SPDK malloc will fail. It will start returning nulls. And in order to allocate more memory, you will have to shut down your application, start it again with more memory pre-reserved, and and then you have a possibility of using too much memory, wasting some of those huge pages, just like on the slides here. All those white huge pages are reserved on a system. They are not usable by any other application on your system, but inside your SPDK application, they are just unused. Yeah, so the challenge is we need to calculate how much memory the program needs upfront. Yeah, and the new memory management was implemented in DPDK 1805 directly in response to SPDK and other feedback, right? It was buggy in DPDK 1805. We've contributed to fixing it. It was stable and complete in DPDK 1808. All the fixes were later backported to DPDK 1805-1. Okay, and with this memory model, all huge pages are reserved at runtime. So when you start your SPDK application, there are no huge pages reserved. You could still reserve huge pages at initialization. You could still provide that command line parameter with some memory size, but you don't have to do that anymore. So now, when you call SPDK malloc, when you create those small allocations, the bucking huge pages will be reserved at runtime, and there will be only as many huge pages reserved on the system as you need, as the application needs. So yeah, it took us some time to implement in SPDK. It's available since SPDK 18.10 and DPDK 18.051. Okay. So if you want DMable memory, you can use SPDK malloc, but there's also a way to register your own memory, to make your own memory DMable. So memory allocated from, let's say, system POSIX, for example. Just calloc or malloc. You can make that memory DMable as well, but there are certain restrictions. So to make this memory DMable, you have to call this one function, SPDK memRegister, on it. Yeah, but that's basically what we call on SPDK malloc memory internally. The user does not have to worry about that. But in order to call SPDK memRegister on your own custom memory, well, yeah, practically you have to use IOMMU if you want to do DMA to local PCI devices. Yeah, we expect this memory to be, if you don't have IOMMU, SPDK memRegister expects this memory to be already pinned, so it's not relocated to different physical memory locations. Yeah. So if you do have IOMMU, SPDK memRegister will take care of setting up a bus address for that virtual buffer. It will do everything it can to make this memory DMable. Also, so far we've only used this API on huge pages or huge page backed memory. So we're only able to register buffers that are 2 megabyte multiple in size, and their address is also a 2 megabyte multiple. So this one is a restriction we are going to lift. We are looking into ways to do that. Okay, and now from the other side of SPDK memRegister, we've got memory maps, basically translation tables from virtual address to any 64-bit arbitrary data. So there are multiple registered maps in SPDK. Yeah, they get notified whenever SPDK memRegister is called. When you create a memory map, you provide it with a notification callback that gets called whenever memory is registered. And from there, you can do anything to make that memory DMable on your specific transport. So for example, we have a PCI memory map that translates virtual addresses to either physical or bus addresses, depending on whether you have IOMMU on your system or not. So inside the notification callback, we will register your memory to do the IOMMU. We will call a bunch of ioctals, actually VFIO ioctals to assign an arbitrary bus address for that virtual memory. And for PCI, we also have SPDK v2fis public API function that provides physical address for any single virtual memory address. And we use that in the NVMe driver and IoT driver as well. For RDMA, we've got a memory map internal to the RDMA transport in the NVMe library. So this memory map provides translation from virtual address to some internal IBverbs memory region structure. It's not available to the user, but it's used internally in the RDMA code. So for every registered chunk of memory, we register, well, we call IBverbs sys function to register that memory. And there's also a vhost user memory map that doesn't have any translation, but is used to get notified of all the new memory registrations and make all the memory de-enable in a separate user space process in a vhost target. Okay, that was my part. Now Ben will go through the dynamic threading changes.
So, there it goes. I'm going to talk about a lot of the changes going into SPDK over the last 6 months or so, about moving to a more dynamic threading model. This is sort of in the same spirit as moving to dynamic memory registration. The problems are sort of similar to, you used to have to specify all the memory you would need up front, and now it just figures it out as it runs. Threads had the same problem. You had to specify a core mask that would, we would spawn one thread per core in the mask and then pull busy loop on all those threads. We want to make it much more dynamic, where we can scale up and down. So just a reminder about how SPDK does threading. This is an updated slide from a presentation at the first SPDK summit. So it's a reminder about how we worked then. The observation is that modern CPUs have many cores, and modern I/O devices, i.e. NVMe, have many queues. And the most optimal way to handle I/O is to assign one queue to each core, and then you can run with no locks or other coordination. And that's exactly what SPDK does. Okay, so the old way threading used to work, as of 1807 and earlier, was we would pin one system thread, a native thread, to each core, and it would sit in a busy loop. And it'd be looking at incoming work, which are basically on a ring of data structures that are a function pointer and a context. And it would just find the next entry in the ring when it gets placed there, call the function, and pass in the context. And so we call that busy loop a reactor. And the messages that are coming in, the function pointer and the context, we would call events. And there was another concept called a polar, which is like an event, but it's just called repeatedly. You don't have to keep sending it. It just keeps going. And there were ways to call those, instead of on every loop through the reactor, you could delay for some period of time, and it would call them periodically. So this worked great for us for a long time. And that was the foundation of SPDK. We would assign data to cores, and we would message pass to manipulate that data. And this is all implemented today in lib/event in SPDK. Okay, so this model has a couple of challenges that all of you have made very clear over the years. The main problem is figuring out how to scale up and down. So during the life cycle of your application, you have periods where you're busy and periods where you're less busy. The goal is to use up to a certain number of cores that you've given it when you're busy. And when you're idle, we want to come back down to as few cores or no cores as we can. And you all understand the benefits of that. We want to save the CPU use, save the power, and potentially give those cores to somebody else who may need them in the moment. There's also some more challenging problems than just bulk scaling up and down the total number of system threads. One of which is rebalancing work. So because SPDK assigns data to cores, usually when we do initial setup, it's difficult to later move data to another core, which you may not just be doing to shut down the other core, but for instance, say I assign 1,000 connections to one core and 1,000 connections to another. And at some point in time, on the second core, or core 1 here, let's say, in the picture, those 1,000 connections are idle. And on core 0, those 1,000 connections are all busy. Right? I have no recourse in the current model to move half of the core 0 connections to core 1. So we call that rebalancing. And then the third and final problem is because we're dictating the threading model here by spawning one thread per core, it becomes fairly difficult to integrate SPDK into existing frameworks, even if those frameworks seem like they would be a perfect fit for SPDK. Many of them likely are a great fit. I'm thinking particularly of cooperative multitasking frameworks, of which there are many, and lots of products are based on schemes like that. So we want to address that as well. OK, so the way we're going to do all of this, or have been doing this, is in a multi-step sort of process that has started to happen in the middle of last year and has continued to happen even up until the latest release and will continue. The first step was to create an abstraction layer between our reactor framework, our event library, and the other SPDK code that we want to separate from that. So we did that. And that library, the new abstracted library, is called thread. It's in lib/thread. The public API is in thread.h. And we're slowly migrating all of our code in SPDK to call this library instead of directly calling our framework. The goal with this library is to make it so that the actual work of scheduling threads onto cores is done by some implementation underneath that initialized this thread library, provided it some callbacks to perform some basic operations. In that way, we can integrate with existing cooperative multitasking frameworks, where they won't use the SPDK event framework. They'll initialize the thread library, implement the operations it needs. I think there's only one operation it needs right now. And then they can use all the SPDK code on their system. So this thread library has been, we've been building to this over time. The thread library itself was implemented entirely in 18.10. So this thread library presents a couple of concepts to the libraries in SPDK. I'm going to go through those now, just so we're all on the same page. The first and most important is an SPDK thread. And an SPDK thread represents a thread. And that's where we tie all of our data gets tied to threads instead of doing locks. So we tie our data to threads. You can send a message to a thread. That's the second abstraction. An SPDK message is a function pointer, and you can send it to a thread. An SPDK poller, similarly, you tie it to a thread, and it just gets called over and over and over again on that thread. You can optionally specify a time delay. And then we also have this concept of an I/O channel. This is effectively a per-thread context associated with some global pointer. And that's simple to say, kind of difficult to wrap your head around sometimes. But the easiest way to think of this is as an abstraction of an NVMe queue pair relative to an NVMe device. So you have some global NVMe device, and on each thread, you're going to create an NVMe queue pair. This is just a software abstraction around that idea. OK, and then we're going to get to the pictures in a minute, which I think will make this a little bit clearer. But before we get to that, there is an important function that we've added called SPDK thread poll. And so historically, we had these reactors that were sitting in a while loop, checking these rings for events and calling the function pointers inside the events. What we've done is we've taken one pass through that loop out, put it into a separate function called SPDK thread poll. And this will run one pass through the loop. It'll check for any expired pollers at the moment of calling, any messages that are sitting in the ring for it to call, and then return. And so then what we did is we changed our reactor implementation to simply have a single local SPDK thread and just in a tight while loop call SPDK thread poll. It also happens to check for the old style events, but that will become an internal implementation detail shortly. That's just for people who are looking in the code saying, you only call poll in the loop. Well, you were not telling the truth. So it is doing more, but that's an implementation detail. OK, that's sort of where we're at with 1901. Now I'm going to do a little future-looking, forward-looking discussion. Before I get started on that, I need to define a few terms. Some of you will be very familiar with these, particularly if you already use cooperative multitasking frameworks. So the terms are, first, a process. We all know what a process is. It's got an isolated address space, scheduled by the operating system preemptively. The second is a thread. That's the standard POSIX thread we all know. It's got a shared address space with the other threads, but it's otherwise scheduled preemptively by the operating system. The next two terms are the ones that not everybody's familiar with. So the next term is a fiber, which is kind of like a thread, but lighter weight, hence the name. The address space is still shared, just like a thread. So all the fibers can see the same addresses. But these are cooperatively scheduled, which means they must explicitly yield. Nothing will stop them from running. They have to return. And these are usually implemented inside of your language runtime or your framework. There's a lot of popular languages that have these implemented now, Go, C#, things like that. Then there's one final term, which is a green thread, which is slightly different than the other three. It doesn't say anything about the address space or how they're scheduled, how they're multiplexed with one another. It just means that this is a thread of execution that's not scheduled by the operating system. OK, so now that the basics are settled, today an SPDK thread is a thread. But in 1904, an SPDK thread will be a fiber and a green thread. That's the big change. So I'll go through a little bit of what that means. The threading library, the new box I showed that was inserted on the diagram, has an initialization function, which has to be called at the beginning of time. And you pass that a function pointer. That function pointer will get called anytime any code in SPDK creates a new SPDK thread. And what that function pointer needs to do is, for whatever the implementation is underneath of the event framework, place it onto some real thread and call SPDK thread poll as frequently as you can. So SPDK thread create calls your callback. You place it onto whatever your implementation is. The implementation shown here is the one in lib/event that SPDK will have, but it doesn't have to be. We dump it onto the list of threads in our reactor. Now, instead of a single thread in the reactor, we have a list. And it just sits there spinning, polling all the threads in the list. All right, so just to recap what we just saw, there's a new call to initialize the threading framework. If you want to use your own framework, you have to call this. If you use the SPDK, lib/event framework, which is what all of our example applications do, it does this for you. Reactors now contain a list of SPDK threads instead of just one. And they're sitting in a while loop polling each of the threads that are scheduled to them. OK, so from here on, we're going to talk about how the threads get scheduled, at least in the SPDK implementation of the underlying event framework, cooperative multitasking framework, which I think is where a lot of the cool opportunities are for us to do a lot better and address some of the problems I had outlined at the beginning of the talk. So as a precursor to that, we have plumbed through all of SPDK the ability for the function SPDK thread poll to have a return value that indicates whether on that particular poll whether it did any work. I have work in quotes, right? So what that really means is that every poller that's registered to that thread has a return value that's supposed to say whether it did anything meaningful or not. And the pollers in SPDK are things like check an NVMe completion queue for completions, or check the RDMA shared completion queue for completions. They're usually checking hardware. And if you don't find any completions, they return false. I didn't do anything. I looked, but there was nothing to do. If they do find something, they say, I found something. I did some work. So we aggregate all the return values for the thread. And then also, if there's any messages that we had to process that were waiting for us when we polled, that counts as work. And we take the aggregate of that answer and we report it up as the return value of SPDK thread poll. So the big idea of advanced thread scheduling is we can use these busy indications to reschedule the lightweight threads. And I've got a picture. So let's say we start out at the beginning of time and we have one SPDK thread on each of 2 cores. And they're sitting there spinning, polling those threads. Sometime later, some code calls SPDK thread create. A thread object is created, and the scheduler just decides, OK, I'm going to only run on core 0, core 1. So I'm going to put it on core 0. You just pick one. And then a little bit later, another one gets created. I'm going to put it on core 1 to keep things balanced. Then we're running away, and periodically we're looking at aggregate stats of how often these things are reporting that they're busy. And let's say everything is looking real idle. Nothing's returning that's doing any work. What we can do is move the threads to core 0. So a little bit about why we can move the threads. We assign data to SPDK threads, and we say you may only access this data while running on this SPDK thread. That used to be a system thread, so it was clear what that meant. Now it's a lightweight thread. It's just some data structure in memory. But it turns out you're only running on the SPDK thread if you're inside of an event that was sent to the thread, or if you're inside of a poller registered on the thread. That's the only time you're actually executing code. Everything is driven by events and pollers in the entire system. So it turns out you're only running code on that thread inside of SPDK thread poll. So if you return, once SPDK thread poll returns for a given thread, I can take that data structure, send a message to another core using the old event message passing system, put it on that new core's list of threads, and it will get polled there. And there's no threading problem. Everything is fine. So we can reschedule work safely using this mechanism. OK, so once we've moved all the threads off of core 1, the key thing here is now core 1 is not doing anything. It has no threads scheduled to it. It can go to sleep. We could also do the reverse process. I don't have animations for the reverse. But if core 0 says, I'm really busy, I'm reporting busy like 80% of the time, we can wake core 1 back up and then send some threads over to it. There's also slightly more advanced scenarios that we're interested in exploring. This starts out the same way. I have, over time, 4 threads get scheduled. I see they're kind of idle, maybe not 100% idle like before. I move one thread over to core 0, and now I see core 0 is busy, 80%. It's not overloaded. It's just right. But core 1 is idle, let's say, or mostly idle. And I need to keep polling the thread, but I don't really need to do it that fast. I'm not finding that much work to do. So there's an opportunity here to do better, and that's have the core slow down. That could mean a couple of things. Unfortunately, on Cascade Lake N skews, there are some new features that we could potentially take advantage of. These were just released. There's a technology called Intel Speed Select technology with two important features. One is called Intel Speed Select technology base frequency, in which you can set minimum frequency guarantees on cores, including turbo. So you could have the one core where you're going to put all the busy work, always have the turbo on. And the other ones always not have the turbo. And then there's Speed Select technology core power, which lets you set relative priorities to different CPUs. So you can say this one's high priority, this one's low priority. The one that's 25% busy, you can set as low priority, and the CPU will, the other cores in the system can take the power budget at a higher priority and go turbo. And it will leave the one is only 25% busy, declocked. And this is critical because we're busy polling. So what we're actually telling the CPU is that we're really, really busy, even though we know it's not finding any meaningful work. So it's really important for us to have this mechanism for us to tell the CPU core that I know it looks busy, but it's not. Don't give it extra power budget. Give it the minimum. OK, and then I'll end on some future direction before questions. We would like to do a lot more with smarter thread schedulers. The one that's implemented in 1901 is round robin. It's not rebalancing particularly well. We'll continue to work there. We would like to do more configuration parameters, including letting certain parts of SPDK have core masks where you can schedule your threads with affinity, like certain threads have affinities for one set of cores and certain threads have affinities for another, and let the scheduler sort of figure that out. And all these configuration options for priorities of cores in terms of power budget and turbo. All right, and with that, we'll do questions.
So on the memory allocation side, one of the multi-process memory allocation requirement was that if two processes wants to share SPDK malloc, they need to be running on different cores. Is that still, that was in the DPDK's documentation. I don't know how true that is, but it was actually written in the DPDK that if two processes need to share the SPDK malloc or DPDK malloc, they need to be running on different cores. So first question is, I don't know, is it true, still true? And secondly, how does that change with the new threading model?
I can say, I don't think there was a requirement that they have to be running on different cores. I think the reason they say to run them on different cores is because they're busy polling. So if you run two busy poll loops on the same core, the performance is awful.
Was that a requirement for memory pools then? Because the documentation was shared between the SPDK malloc and memory pools.
They have to be in the same memory group, which doesn't have to do with cores, right? So that just has to do with, we flag which processes should map each other's huge pages, right? Okay. It's just the -I parameter to all the SPDK apps. And they have to be in the same memory group, which means when they start up, they'll look to see if there's somebody else in their group and map all their huge pages, right? Okay. With the threading stuff, nothing has changed on the memory front. It's the same requirements.
Okay.
Hi, I have a question about thread schedulers. Like the one that is currently SPDK have is that, so a scheduler doesn't kind of define that when or how many threads should be, spawned on which core, or if we want to move one thread from one core to another, so should we do it manually? User should define it, or is there anything that a scheduler can kind of do it automatically?
Well, so I think the ultimate goal is that the scheduler is automatic. But certainly people for their own applications are going to want to use their own framework often, and they'll do the scheduling of the lightweight threads themselves in whatever cooperative multitasking system they have. But for the SPDK applications, the default implementation, the one that's checked in for 1901 is basically a static scheduler. It just round robin hands out the threads and never moves them. So we're going to make that much more dynamic, where maybe like once a second it will see how busy each thread is, make some decisions, move some things around. The idea is that it's all dynamic, all done by code, not by, you don't have to code anything to say move this thread here, et cetera. Kind of like real threads in the operating system.
Thanks, Ben, Dariusz, for the presentation. With the new threading model, I was wondering if there's any API or is there a way to detect the core lockups by any chance?
You say core lockups?
Core, yeah.
And you mean like some thread
Like
did a blocking operation?
Yeah, like CPU is busy for a long time.
So we're all in user space, so we can't like preempt the thread and do anything about it. We could certainly report metrics of how long SPDK thread poll took, and if it takes a very long time, it should get in and get out every time you call it, more or less. And so if you're seeing it take a very long time for one thread poll, that's a problem. Your code is not being cooperative, right, in the cooperative multitasking sense. And we could definitely flag that and report it for you. But we don't have the same power as the OS scheduler. I can't stop it.
We usually don't have any while loops inside pollers. Poller itself is run in a while loop. So usually the worst thing it can do is to be called continuously and return. There's still some work to do, something like that. But there is no case, or we try to avoid cases where a poller can lock up.
To determine that a core is 80% busy, or so that you need to move the thread to another core or something like that, are you relying on OS statistics to determine how busy is it or how idle is it?
Yeah, so there's two ideas floating around for how to determine what busy is. I always say whether they did work, quotation, like these are not well-defined concepts, and so one is to use the return value, and keep stats on how frequently we poll it and it returns either of the values and compare. That is certainly going to be a nonlinear scale, right? Returning idle 50% of the time doesn't mean you can do 50% more work. You're probably, like 50% is probably high, so we'll have to sort of figure those things out. That's the main challenge, is figuring out what busy is. The other idea I heard was actually from the DPDK team, and it was really clever, and that's at the beginning of the application, what you can do is before any events or pollers are scheduled to the threads, just spin for a very short period of time, calling SPDK thread poll, and measure how many times you get through the loop in a second, or some time slice, just so you have an idea of what real idle is. And then in reality, when you're actually executing real code, you're going to get through it some fewer number of times than that per second. And you could also use that as a metric to figure out how busy am I, relative to what I know to be idle. So those will probably get combined, and we'll do both, and it'll all be heuristic based, and it will just sort of move things around as best as it can.
Follow-up. Just a short one. Is when you are moving one thread to another core, is it like NUMA aware, or?
It should be,
Okay.
but it's not today. Right now, it's just moving into any core you've set up on your system. But that's certainly one of the things we want to set up, where each thread could individually have affinity masks that the scheduler attempts to respect.
Okay, so we've got one back here, one here,
I have a
and
question.
then one here.
Okay. Is
Can
there
you
a way
hear
to
me?
transparently, integrate with ePoll or some of them where, as an application, if I'm looking for a notification from a file descriptor, which is not even SPDK data path, but could be some network, and can I integrate with the SPDK poll?
I mean, that's how the network transports for like iSCSI and NVMe Fabric work today. They're both using ePoll. and they're all on non-blocking file descriptors. So we just do like an epoll wait on a non-blocking file descriptor, and it tells you which things are busy, and if it doesn't, it returns. So you can never block in the SPDK system, but you certainly can use epoll within, a poller, and if you find something, return that you found something, and if you didn't, return that you didn't, and it will just work out.
The question is, I think now you have scatter gather lists, so you have the memories are pinned down, but they could be from different cores. And how does threading and scatter gather list work when the memories are not on the same core and you are moving the scheduling to a different core?
So the memory pools are usually allocated out of global pools using a memory pool data structure, which any thread can access. It's based on a ring, so you can actually, it's just an atomic to take something out of it. We actually do often put in thread local caches of data buffers that are associated with an SPDK thread, not a real thread. And that's for performance reasons. And so the cache will move with your thread as it gets rescheduled. But the memory, when it gets allocated, is claimed basically by that thread, and then the thread will give it back when it's done. So you can move the thread around, and the memory goes with it. The data is always associated with an SPDK thread. It will only ever be used from that SPDK thread. Even though it may get rescheduled somewhere else, it's never running on two real cores simultaneously.
Does the dynamic memory allocation model introduce any sort of performance overhead compared to the static model?
It does. Memory allocation is really expensive, especially if you have multiple applications sharing the same memory. Every allocation may trigger internal IPC to allocate that memory in another process, then get the completion. So yeah, memory allocation is more expensive, much more expensive with this model. But we don't do memory allocation at runtime. There's this handy SPDK mempool you can use to pre-allocate your memory, have a memory pool, and then use that in your application.
Hey Ben, Rahul here. So with this changing threading model, so the structures and the affinity to the code, those changes. So I'm just thinking, is there any difference in what we would see in terms of error handling or management related issues, and how you would say free up a resource? For example, say when you want to free a queue pair in RDMA level, it's one thing I'm thinking of. Would you see any issues or challenges there?
So all the vast majority of the libraries in SPDK, with only two exceptions, and it's a little bit of code in iSCSI and a little bit of code in vhost, we're already associated with an SPDK thread, and so this change to where we can move an SPDK thread around happened entirely transparently with no changes to the other libraries. So the short answer is nothing changes really. It works exactly the same way. It's just the system thread that happens to be executing at the time of the SPDK thread may change periodically. So the errors are all the same.
All right, this one maybe is a simple one. So with all these SPDK threads being dynamically moving around the cores, so what's the current limitation of the list of all these threads in each core? Is simply power of 2, or is it dynamically can be expanded, or there's a fixed value so far?
It's a linked list, so you can have as many as you want. But in practice, again, we're assigning these important control structures and data structures to the threads. Your NVMe device probably has 32 queue pairs or 128 queue pairs or something like that. So there are limitations there where you can't create an NVMe queue pair on a new thread because you just ran out of available queue pairs. Some of those are things we'd like to try to address in software where, maybe if we can't get an NVMe queue pair for a particular NVMe device, but we can get it for the rest of them, maybe we still create the thread and just bounce through that thread to one that does have a queue pair. We'll figure that out over time. But the limitations are primarily driven by the storage devices and the NICs. Other than that, it's just memory.
Thanks.